Alright, welcome back. This is section 13.3, which is using pressure and measuring pressure with different devices. And so in the previous section we talked about pressure in the depth of a liquid as well as force as a kind of indirect measurement of pressure in a liquid, and that's related to the area of that. And so I have some bad news for you starting section 13.3, which is that I lied, and I'm sorry, but I had to. So pascals isn't the only unit of pressure that we use. In fact, it's far from it. But I introduced that first because pascals is the SI unit of pressure. And so when I'm asking you questions, I need you to put that in the SI unit. However, pressure relates to a lot of different industries and a lot of different uses, and everybody kind of has their own terms. And then we also have with it to mix up the United States using the standard system. And so the typical measurement that we use to talk about pressure is an atmosphere, represented by an ATM. An atmosphere is the typical usage because it talks about atmospheric pressure, and we live in the atmosphere, and so that's a practical measurement. So atmospheres right there. But do know that that's not the SI unit. And so what I've got here for you is kind of a table of conversions. This is also in your book. We've been talking about the Pascal, and this is the conversions to 1 atmosphere. And the interesting thing I want you to note here is that this 101.3 kilopascals, we've talked about that as being the pressure at sea level. Also note that the pressure at sea level is 1 atmosphere. And so you can see that this atmospheric pressure is a lot more intuitive than things like kilopascals, which is also why we use this. This is our general term. When we talk about pressure, a lot of times we're talking about weather, and in weather we use mercury as an indicator in our instruments. And so the rest of the world with the metric system uses milliliters of mercury expressed as mmHg. Hg is in the periodic table for mercury. And 750 millimeters of mercury, or milliliters, I'm sorry, of mercury is equal to 1 atmosphere. Consequently, in the States, we like inches, and so 29.92 inches of mercury is equal to 1 atmosphere as well. And then in industry and engineering and mechanics and things like that, they tend to use pounds per square inch, which is represented as PSI. If you're a scuba diver, you recognize this as a tank of measurement of pressure for tanks. If you own a car, you should recognize this as a pressure in your tires. And so the equivalent to atmospheres is that 14.7 psi is equal to 1 atmosphere. And using all of these conversions, we can happily convert between units. So I can get psi to pascals, or I can get mercury to pascals, or I can get atmospheres to pascals, pascals to atmosphere, all kinds of fun stuff. But hopefully I'm not going to make you do too much of that. I mostly want to talk about how we measure pressure and why pressure is important. So chances are, if you've ever watched the weather, you've seen a map like this. We know that when fluids are moving, which includes our air and air systems, when fluids are moving, the pressure can change. And so we talked about earlier in chapter 12, we talked about convection currents, right, where the hot stuff rises and the cold stuff falls, and this is what creates our local winds. Local winds make air move. Moving air has different pressures. And so meteorologists are very interested in where are the low pressure systems, where does air have the lowest pressure in the States, and where is there a high pressure system. High pressure systems can tend to push weather away or keep weather away from it. Low pressure systems tend to draw air into that area, and where there's a mixing of air and temperature, a lot of times we get storms. With our global winds, what we see is that these move from west to east in that typical pattern, and so weathermen are very interested in pressure, especially atmospheric pressure. We use 2 instruments to measure pressure, manometers and barometers, and so I'm going to talk about each as well as how to get the pressure out of those. A manometer is a device used to measure an unknown pressure of a gas. And so typically what we have is some kind of reservoir over here. We use this in industry a lot to talk about pressure within a piston. And so we've got this kind of unknown pressure going into the system, and we've got this little U-shaped tube. And we allow that pressure to exhaust into the system. Within that system, typically we have mercury, but you can put any liquid with a known density in there. And so if this has a high pressure, it's going to push down on this, causing that pressure to be exerted through the whole fluid, and what we see is a rise in the fluid on the other side. We express this rise as a delta H. That delta H acts an awful lot like a formula that we know with depth. And so if this is rising, then H is going to have a positive value. If for some reason this is a low pressure system, it is going to draw this liquid up, and that liquid is actually going to be lower than what it started, which would be a negative H in this case. And so if we want to know the pressure of that unknown gas, we can take 1 atmosphere plus the density of the liquid that we're using, gravity, and the change in height, whether that's positive or negative. What this looks like is if there is no change in height, right, and we're looking for the pressure of that gas, we get the initial pressure plus density GH. There is no change in height, so this term goes to 0, and that has a pressure of 1 atmosphere, right? And we can also talk about that in terms of pascals if we want. If that pressure is pushing down, that liquid goes up, and I have a positive H, right? And so that's going to be a pressure greater than 1 atmosphere. And if the pressure in that reservoir is very low, and that's what we call very low, and that's what we call a vacuum, it's going to suck that fluid up and cause it to drop on this side, which is going to give us a negative H value, okay? And we always measure from the top of the one on the left to the top of the one on the right, and if the left one is higher, we're looking at a negative value. And so as an example, an engineer is using a manometer to measure the pressure of an unknown gas. If the pressure raises the mercury in a manometer by 5 centimeters, what is the pressure of that gas in atmospheres, right? And so what I'm looking at is my typical formula equals P naught plus density of that liquid, gravity, and the change in height. And I know here, where is it? Let's see. It's raising the mercury in the manometer by 5 centimeters. And so if I'm going to draw a graphic of this, I've got my unknown gas, right, which is feeding into this U-shaped tube. And I know I've got mercury on the inside. My H is here, and my H is going to be positive in that situation. And so I know that I'm going to start with 100 and 1,300 pascals plus, and then I know that the density of mercury is 13,600 kilograms per meter cubed. Gravity, always 9.8. And the change in height, I've got an expression in meters. I've got 5 centimeters. So that's going to be 0.05 meters, okay? And when I do that calculation, I get 107,964 pascals of pressure, but notice that my problem is wanting this in atmospheres, and so I need to look at that conversion factor. And I know that 1 atmosphere is equal to 101,300 pascals. And so what I'm going to do is get this to atmospheres. I'm going to do 1 atmosphere is equal to 101,300 pascals. My pascals cancel, and I'm going to be left with atmospheres. which then gives me a pressure of 1.07 when I'm rounding atmospheres. And so if you got that, great job. Nice work. We're going to go on and talk about barometers. And so barometers, you've probably made one of these in elementary school. And in elementary school, what you probably did is took a cup of some sort and stretched a balloon over it and put a little straw on top, right? And when you go up in elevation, the pressure is decreasing, and so what you'll find is that little balloon blows up, right, to indicate an increase in pressure. If you go down in elevation, it's going to decrease, and what you're going to see is a dip in that little balloon. Barometers work very similarly. They're used to measure gas pressure, usually atmospheric. And so what we look at is that the pressure, atmospheric pressure, is equal to the density of the liquid, gravity, and the height of the column. And so how a barometer is made is that you take something that looks like a test tube and you fill it to the brim with a liquid. You then place it upside down in a dish of some sort, right, and allow water to flow between the two. When the atmosphere pushes down on that outside water, what we see is an increase in this. When atmospheric pressure is low, that water is allowed to rise because the pressure on the outside is less than the pressure of the water. That water rises, and consequently we see this drop, right? And so when we're talking about the height in a barometer, we're talking about the height of the liquid from here to here. And so what I want you guys to do is go ahead and try number 17. You can pause the video or you can go along and work with me. And so in number 17 it says the container shown in figure 13.17 is filled with oil. I know that oil has a density of 900 kilograms per meter cubed. Okay, I actually don't even need to know whether that picture is a barometer or manometer. I can just use what I've been using, and so I know that the pressure at some depth is equal to the initial pressure, density of liquid, gravity, and the height of that column. For this particular one, we're going to use height as the depth of that column. And so at point A, that is 50 centimeters down, right? And so we're going to use 101,300 kilopascals. Density of oil is 900 kilograms per meter cubed. Gravity is always 9.8, and the height of that column is 0.05 meters, which should give us a pressure of exactly 105,710 pascals. Whoop! Sorry for running away there. If I want to then know the pressure at point B, and I know B and C are the same because they're at the same depth, then I can use that same formula to find it. And so pressure equals the initial pressure plus density, gravity, height. I'm going to do the same thing, 101,300 kilopascals at that pressure. Oil is still 900 for the density. Gravity is still 9.8. Only this time I'm looking at a depth of 1 meter, and so I get the pressure at point B to be, let me see, what is it, 110,120 pascals. And when I do the difference between the pressure at point B and the pressure at point A, right, the difference in the pressure is going to equal 4,410 pascals, which I can then get to atmospheres if I want. And if you got that, good job, touche. You're doing great. Keep up the good work.